Hello everyone. Today we start with the idea of superconductivity. Just to put this into context in our course. So far we have studied how a simple electron gas, once we put interaction amongst the particles, how their properties change, right? So in our StatMech course, we have all read free electron gas, properties of them, thermodynamic properties. And then we introduced some interaction, Coulomb interaction amongst the particles, and we explored how things can, how such an interaction affects the properties, right? Okay, so in our treatment, we have mainly um, taken recourse to perturbative schemes, right? So in the sense that we kept the strength of the interaction small so that we could carry out things mostly within the perturbative regime, and we figured out how within that regime certain properties change, and there were very interesting properties which came out. But that sort of is only a very minuscule portion of what the beauty of the subject is, because uh, in condensed matter systems, or even in solid state systems, a subgroup of all condensed matter systems, let's say give you a solid, a variety of interesting effects come, which are mainly um, related to phases of matter, or in other words, things that are not perturbative in that sense. So in some way, when we're doing perturbation, we are assuming that whatever the system is to begin with, so if the system is an electron gas, it remains so, only things change a little bit. Okay, and that is what exactly we found out in our treatment of electron gas. But there are situations, and which is perhaps more interesting, these situations are when we turn on interactions, and by now we know there is not just one interaction. In a solid, there are so many kinds of interaction, between the electrons, ions, between the ions, and if there are other degrees of freedom like spins, they will start talking to each other. So there are all kinds of interactions, and they can eventually lead to a scenario where things are not just a little bit of change from where you started. It becomes a scenario where, because of these interactions, the very notion of what you started with completely changes, and this is what we call a new phase of matter. We are all familiar with these things in our day-to-day life. So for example, water turns to ice, then it melts to water, and then on heating it becomes gas. Fundamentally, it is changing some symmetry, giving rise to new phases of matter. So what is the equivalent in a solid state system? In this course, we are going to learn or deal with the most two well-studied and most common phases, which are superconductivity and magnetism. Of course, this is far from comprehensive or exhaustive. Practically, there are infinite number of phases that are possible, and some of them are the things that are most commonly studied. Of course, is superconductivity and magnetism. So what is a superconductor? Well, by the very name and by our, from whatever common sense we have all read about superconductor at some point or other. It is obviously something that conducts with zero resistance, right? Now, you see, in a Drude model, we all know what a Drude model is. We did it in solid state 1. So the conductivity we know is a very simple formula, which is ne square tau over m, where n is the number density of charge carriers, E is the charge. Tau is the scattering time, or the mean time for the electrons that they get scattered, which leads to the resistance to begin with, and m is the mass of the carriers. So one can then ask, well, then if superconductivity has zero resistance, meaning infinite conductivity, is it that a superconductor is simply a metal with tau going to infinity? Meaning, let's say I make a metal purer and purer so that there is hardly any scattering anymore, because at the end of the day, it is scattering which gives rise to resistance. Then is it that if I can go to the limit where I can take all the scattering centers away and there is no scattering left, then the conductivity will tend to zero, and that is what a superconductor is? The short answer is no. it is not simply a metal which conducts enormously large because your metal is very pure. It is fundamentally a new phase of matter, meaning the metal you started with has undergone a drastic transformation and has become something completely new. And resistance going to zero just happens to be one of the properties, which is non-trivial. There are several other properties, all of which manifests what is called a superconductor. Okay, so let's discuss some of these properties. So the first, of course, is the zero resistivity. So if I take a normal metal, I know that resistivity typically in a metal increases with temperature, because the more higher the temperature, more scattering will happen, right? In a superconductor, in the normal state, of course, it also does the same thing, but at some temperature called the critical temperature, denoted by Tc, the resistivity suddenly drops to zero and then stays zero. This is what the hallmark of a superconductor is. But this is not the only property. Some of the other hallmark properties of a superconductor are, for example, persistent current. So, for example, I take a ring of a material, let's say a superconductor, and then I start putting some flux through. Now we know that a changing flux will generate an EMF. As a result, current will start flowing. Now the thing about a superconductor is that once I have shut out the source, that is, I've started a current and then I take out the flux, no more change of flux, this current should continue till eternity. It should not die down. That is, it is truly something that does not dissipate energy. Okay. Then the third property that a superconductor should exhibit is, again, I'm sure all of you have encountered this, something called the Meissner effect, which is perfect diamagnetism. What does that mean? Well, we know what a diamagnetic system is. Very simply, I take a system, I apply magnetic field, whether the system allows the field to go or does it shun it, does it avoid it, right? So that depends on how the system is reacting to it. Okay, so if it favors the field to go through it, then it is simply a paramagnetic thing, and if it does not allow, then it is a diamagnetic thing. So in a normal metal, it would allow the field to penetrate, but in a superconductor, it expels all field so that the field just circles around the lines of the field, and it does not let it go through the superconductor when the system is a superconductor. Or in other words, if I were to draw the magnetic susceptibility curve versus temperature, so there is some susceptibility as a function of temperature. I have just drawn this schematically. It does not need to be a flat line here. But the main message is that it is positive for certain temperature, and then bam, once it hits the critical temperature and the system becomes a superconductor, you will see chi will become negative immediately. -1 is normalized appropriately. Or in other words, what this means is that the field that is penetrating, that is inside, is essentially a sum of the external field and whatever the internal response field that has been created due to the magnetization. So superconductor is a perfect diamagnet, meaning that yet it creates exactly the same amount of field that you would put from outside, but negative in value, so that they will cancel and there will be no field inside. Okay, so that's the whole point. That is why susceptibility in properly normalized will be -1. Okay, all right, and finally, another very crucial signature of a superconductor is, in fact, one of the most counterintuitive ideas that you will encounter is something called an energy gap. What do I mean by this? So, and this in fact is one of the truly separating feature from a conductor with very high conductivity and truly a superconductor which has undergone a phase transition. What do I mean by energy gap? Well, even though a superconductor conducts a lot, there is infinite conductivity. Surprisingly, if you measure other kind of characteristic observables, it will actually sort of emulate or mimic an insulator, and this is very counterintuitive. Now, what is an insulator? An insulator is, in the band picture, essentially a scenario where you have no density of states near the Fermi level, right? The Fermi level lies in the gap. That means, and we know what are the signatures of an insulator, because there are no density of states at zero temperature. Most observables such as conductivity and specific heat and so on and so forth, everything will be zero because there is no carrier to give you that observable. Which means once we increase temperature, remember your semiconductor physics, once we increase temperature, things will get excited from valence to conduction band, and most observables, that's why, vary as this Arrhenius law, which is exponential, e to the power minus delta over t. This is nothing but simply reflecting that the particles are getting excited from our lower valence band to the conduction band, and delta is the typical gap. Now the funny thing is that although in a superconductor it is conducting fantastically well and it is showing perfect diamagnetism and the other properties that I mentioned, persistent current and so on and so forth, in certain observables it actually mimics an insulator. For example, in a normal metal, if I were to measure the specific heat, we know that if we forget about the lattice part or the phonon part, just the electronic part, we know that specific heat is varying linearly with T, so that C over T is a constant with T in a normal metal. If you were to do this thing in a superconductor, you would see that as T goes to 0, this thing actually goes to 0. And then it rises and then suddenly finds a very sharp change, a sharp discontinuous drop at Tc, and then starts mimicking a metal. So in this region, it is nowhere near a metal. Even more interesting is something called a tunneling conductance, which is essentially you are trying to, I give you a sample, you have some tip through which you try to pass current locally on that sample. And if there are no states at a given energy, then you will not see current going through locally from the tip. So then you can measure, you can calculate the tunneling conductance, and bias is essentially how you are, at what energy you are keeping your probe. Okay. Now, so you can think of this bias essentially as a proxy for the Fermi level in some sense. So in a metal, because my Fermi level is in the conduction band, as I change my energy, everywhere there are carriers. So there is a perfect conductance, which can change with the voltage, but there will be some non-zero value. Here you see this guy here, as you change the voltage, right where your Fermi level lies, which I am denoting by 0, instead of showing you a finite conductance, it actually shows you completely zero conductance, telling you that there are no carriers at all present at this zero energy. And you keep scanning the energy values at certain energy. By the way, this is all happening below Tc, right? It is a superconductor. So this is what would happen above Tc, and now I have made this a superconductor below Tc, and I'm doing the same experiment. This curve has changed into this, which is for certain energies around the Fermi level, there is no conductance at all, and then suddenly you find lots of density of states around, suddenly a sharp jump, a discontinuous change here, and then these regions are same as here. So this is fundamentally very perplexing, right? I have a system which on the whole is conducting fantastically well, telling you as if there are a lot of carriers and there are hardly any scattering. However, when I try to actually probe how many carriers are there, this experiment is telling me there are no carriers at all. Okay, so this is fundamentally very interesting feature of a superconductor. Okay, just to continue with the basic idea. So here I'm just giving you an overview before I get into the meat of the theory. Okay, so generally speaking, there are two kinds of superconductors. It goes by the name of type 1 and type 2. And what are those? Essentially, a superconductor is a very shy object in some sense. Why do I say that? Because it does not handle too much disturbance. For example, if I pass a lot of current and a lot of magnetic field, then all these statements that I was making earlier, that I pass current, it goes through with infinite conductivity. I pass field, it is completely shielded and it cannot enter. These statements are valid only up to a certain strength called the critical current or the critical field. That is, if I really crank up the strength of the current or the field that I pass through, the superconducting state breaks down and it becomes a normal metal. Okay. Now it is here that different superconductors behave differently. That is, at what value and how they break down. So type 1 is a scenario where you start applying a magnetic field. For certain strength of the external field, it perfectly shields the external field. So it's a very nice superconductor. And then at some value, it completely loses that and it becomes a normal metal. But this is not what is observed in all superconductors. And this is where type 2 comes in. So type 2 superconductor is something that has the same feature up to a certain critical field, which we call the lower critical field, HC1, up to which it behaves exactly the same way. The magnetization changes as -H. But then it does not immediately gets its superconductivity destroyed, or rather it gradually changes back into a normal metal. Okay. So the region between this HC1 and finally the field at which it truly loses all superconductivity, this is called the upper critical field, or HC2. Now this particular phase in which the phase between HC1 and HC2, this is called a mixed phase. This is a very interesting phase because unlike here where it is a perfect superconductor, this is a region where the superconductor is a mixture of normal metal and a superconductor. By which I mean the following. So if you take the sample and you are somewhere here in this particular phase, you will see that if you apply a magnetic field, it is not completely shielded. A part of the field is shielded and a part of the field goes through. Finally, when you are above HC2, entire field goes through and it has become a normal metal. A very interesting feature of this is that when it allows the field to go through, it does not really allow uniformly over all space. So it forms tiny little pockets, which I have denoted by these circles. These are called vortices, through which the field is allowed to penetrate, and in the intervening regions, the fields are not allowed to penetrate. So it is as if the whole superconductor has become separated into regions of tiny islands through which field can go through, and regions which are perfectly like the superconductor before, where field does not penetrate. Okay. And even more interesting is that these regions, these holes through which the field are allowed to penetrate, these regions form actually a perfect lattice. What kind of lattice, what geometry, what pattern, that entirely depends on the energetics. Okay, essentially the lattice is formed because the system wants to minimize the energy. That is something that is beyond this course. I don't want to get into that, but this is what is called a Abrikosov vortex lattice. Okay, good. So that is a sort of very nice overall picture of what a superconductor is. Now let's go through some experiments. Okay. So far I've given you an idea of what you expect. So it is always good to refer to actual real experiments to see, I mean, how much they actually are seen in real material. So this is the first paper, the first ever discovery of superconductivity by Kamerlingh Onnes, as you probably are aware, a Dutch physicist from Netherlands. So pretty much accidentally, he figured out that he was doing low temperature measurements on mercury, and as he was reducing the temperature right at 4.2 Kelvin, he figured that suddenly the resistance completely dropped to almost insignificant resistance. At first he thought it was all wrong, or he was making a mistake, but it soon turned out that this was a reproducible feature and it was a real phenomenon. So this is how superconductivity was discovered, right? So that's our first feature of superconductivity. Okay, second, as I said, that in a superconductor the susceptibility has to go from positive to largely negative. Of course, here things are not properly normalized. That's why this is not -1 as I had shown before. But the key feature is that it has become large and negative. So this is exactly what is being shown. So this is another paper. This is some different superconductor. Here you can see that at the same temperature at which the resistance drops to 0, right around 81 or around 85 Kelvin, you see around the same temperature, you see a similar transition in the susceptibility. It starts becoming negative. This concomitant presence of these two features is what defines a superconductor. Just alone this wouldn't really be a convincing proof. Okay, let's go to the third defining property. As I said, one of the most perplexing properties. Here I show you the differential conductance which I was talking about earlier, the tunneling conductance. And you see essentially this is some observable that measures how many density of states are there in your system. And you see exactly at 0, that is where the Fermi level lies, there is hardly, so 380 millikelvin is when the system is perfectly a superconductor. Okay, so you see that there is no carrier density at all for a sizable portion around the Fermi level. So at these energies there is no carrier, and then suddenly, as if you go slightly away, and at these energies there is a sudden discontinuous change, and then again the thing happily behaves as a metal. So what is this thing? And of course, as you increase temperature, you see the thing becomes completely metallic, meaning the superconductor has changed into a normal metal. That we do expect, because beyond Tc, superconductor will change. So what is it that that is producing such a feature? Why is it that in a superconductor near the Fermi level there are no carriers, there is no density of state? Okay, next we have an experiment showing you the specific heat. As I said, C over T will show you interesting features. The first feature is it will start from 0 and move up, and then at Tc, as you see at 1, T over Tc, it will suddenly give you a sharp drop, and then it will level up and become metallic. So this is also again seen in niobium sulfide, which is again a superconductor at certain temperature, below certain temperature. Okay. Okay, finally we have the picture of what is called the Abrikosov flux lattice, as I said. So this is an example of a type 2 superconductor, and as you see that here they are scanning, again doing this same thing. They're trying to scan the tunneling conductance, meaning they're trying to see where they have carriers and where they have not, density of states. And as I said, if you are in a mixed phase in a type 2 superconductor, certain regions will become normal, certain regions will become will stay as a superconductor, which means if you are trying to find the density of states in certain regions, you should see density, and certain regions you shouldn't, right? And here you see very nicely how this has broken up into tiny islands, where in some regions there are and some regions there aren't, meaning it's a mixture of superconductor and normal metal. And not only that, you see how nicely this has formed a triangular lattice, the regions which have become normal. Okay, as I was saying earlier, this is what is called an Abrikosov flux lattice. Okay, just to round up this brief idea about the overall picture of superconductivity. So before we get into the theory, it's good to have a sort of a little sense of how the history progressed, so that we have a sense of, you know, what was so challenging and why a theory is considered so fascinating or so remarkable when one was proposed. So this all started in 1911. As I said, Kamerlingh Onnes discovered superconductivity. So this was experiment. In 1933, Meissner and Oschenfeld, they discovered the Meissner effect, which was also experimental. And then soon thereafter, in 1935, London and London, from the same family, they gave the first theory, which was a phenomenological theory. We'll do it shortly, to sort of explain these two together, why resistance can go to 0 and there can be this complete screening of magnetic field. Thereafter, in 1950, on the Russian side, on the Soviet, as it was called then, Landau and Ginzburg came up with another phenomenological theory, which is now called the Landau-Ginzburg theory, an eponymous theory, which essentially was one step more than what London and London did. although it was phenomenological, it could explain not only what London and London explained from these two observations, but also things, for example, the specific heat and other thermodynamic signatures, which this theory could not. And finally, 1957 is something that you must have all heard, the BCS, the famous BCS theory, which takes its name after its creators, the Bardeen, Cooper, and Schrieffer. And this was the first truly microscopic theory, meaning a theory that was written down starting from a microscopic Hamiltonian, from where all properties of superconductors could be derived. And this could explain all these that London did, whatever Landau-Ginzburg did. In addition, it could also explain that gap, why near the Fermi level in a superconductor you do not have density of states, and why they appear at finite energies. So that was a real triumph of this theory. Okay, and fast forward. So this went up. Of course, I'm giving you a very brief and very sketchy outline, just the sort of the bullet points or the main developments in this history. There are a lot of subnotes and footnotes that should appear between these dates, because a lot of other works also happened in the intermediate times. So the next big deal was in 1986, where Bednorz and Mueller, they discovered a superconductor with a very high TC, or critical temperature. So remember, these were all around less than 10 Kelvin. So 4.2, 5, 6, 1, it's all around that. This was, for the first time, it was on the order of 10 to the power 2 or 100 Kelvin. On that order, this was discovered for the first time experimentally. And of course, just like them and them and them, they were also awarded the Nobel Prize for their discovery. And after that, other people also discovered a lot of other such materials. For example, Chu in Houston, and then even as late as 2008, a new class of materials were discovered where these kind of superconductors with high temperature, critical temperature, were discovered. Now, I should just mention a little bit what exactly is meant by high critical temperature or high TC superconductor. Of course, from practical point of view, a high TC is very much desirable. Then you can put superconductor to practical use at room temperature. But from a physicist point of view, what we really mean by high TC and why it is so interesting to us is more than that. It is not just that this TC is 100 and this TC is 4. What we are really interested in, and you will get to know shortly, this difference is that the basic fundamental mechanism that dictates the origin of the phenomenon in these class of materials is fundamentally different. What leads to the mechanism here, it is not the same. And this is why this is fundamentally different. Although both are superconductors, fundamentally this is a new class of material. And honestly speaking, the theory of this class of materials is still an active area of research. There a lot of effort has gone through. Some of the biggest names have been working in this field, yet there is no consensus on a truly unifying theory that can explain superconductivity in this scenario as BCS did in this scenario. Okay, so in that sense, this is still an open problem. Okay, so that ends our general introduction to superconductors. Just to give you a sense of what we'll be doing next, in this course we will be mainly dealing with this microscopic theory, because this is our main goal in this theory. Okay, of course I will do very shortly the two phenomenological theories just to get warmed up and also to give you a sense, but I'm sure in other courses you will come across these kind of treatments. It is this that is we are most equipped to do it in this theory, because now you know second quantization, you have dealt with interacting system, so we will be really able to do this in full rigor properly. Okay, so that's what we are going to do. Next lecture I will introduce these things to you, and then in the following lectures we will dive right into our BCS theory. Okay, so that's all for today. See you guys tomorrow. Okay, bye.